All right, good morning, everybody. Like, we're now all walking into class exhausted and not talking anymore, so glad we finally hit our stride here at 8 in the morning. So last time we spent, I don't know, most of the class, you guys spent deriving what we call the fin equation. So hopefully you got there kind of to the right final answer. What we're going to do today is look at a couple scenarios where we would actually use this. Right, so our fin equation is 0 plus d dx ac dt dx minus e hc t minus t infinity. Okay, so hopefully you got to something either that or like that last time. And I think from walking around, we all did. I don't know, hopefully it was helpful to at least see a little bit where that came from and how we can take fundamental things like energy balances and kind of use those to build up a differential equation like this. It doesn't just appear magically. We build it from pieces by saying, okay, what are the important things? And let's take a slice of it and see what's happening going in and going out. And how can we represent that in math terms? And eventually we can get to something like this. Right, we're looking here at this equation, right, for something that came from, a system like this, where we had obviously our fin, and then we took a small differential slice, dx, and said, right, there's conduction happening in this direction. So this is like Q, we call that QX and QX plus DX. And there was convection happening at the outside, Q convection. So this is why you get these two different area terms. Conduction is happening along the cross section. Convection is happening at the perimeter of our object. Okay, so there are a couple assumptions built into this, though. Like every engineering model, in order to get an equation like this, we had to build in into the model some assumptions about how reality works. So our assumptions for a fin and we didn't lay these out in as much detail when we were doing it last time, but I think hopefully you're like, oh yeah, I guess we did say that. The first assumption is that convection is constant at fin surface. Right, we're saying that the convection coefficient is just a number, and it's that number, and it's the same everywhere. The second major assumption that we had to build into this model was that the temperature only changes down the fin. In the x direction. So what we're saying is that that entire cross section if we took a slice, the entire cross section is the same temperature. It's the fin's not like hot in the middle and cold at the edges, right? If we took a slice, right, this would be a cross section. This is say Y and Z. If we took a slice, the temperature of that whole slice is constant. It's the same. So the only temperature gradient, the only change in temperature is in the X direction, is from the base to the end of the fin. So this is a reasonable assumption as long as our fin is thin. So this is the, so right. Or not constant, is the same. Okay. So this is the thin fin assumption. So this is good for high K. High thermal conductivity materials like metals. It's good if for, right, if this is the height, well, I don't know, we'll call it B. Thin fins, a small thickness B. Because you need, basically what you can't have happen, you can't let heat get stuck in the middle. It has to be able to very easily get to the edges. So high thermal conductivity, that means heat can very easily flow to the edges of the fin. Or if it's thin, the edges are close by, so you can very easily flow to the edges. So these are kind of the two major things, because we only considered, right, if you look at our differential equation, temperature is only changing in X. We only have the dt dx. It's not changing in Y or Z. So that was an assumption that we made. It's often a pretty good assumption, because if you think about these systems, we typically design them so that both of these things are true, or at least close enough to true that we can still get good answers. So for a lot of this kind of modeling, we're not necessarily looking at getting the exact right answer. You're looking at getting, for this type of modeling, you're looking at getting a pretty good answer that can help you design something and help you to think about how you would design it better. Right? You might throw your final thing into a CAD model and get a better answer, but this will help you think about, okay, where are the weak points in my design? How could I do it better? What should I be modeling in CAD? So hopefully it can help you build a little bit of intuition about how this stuff works. Okay, so those are the fin assumptions. So to just solve an example problem, because actually solving this differential equation is not trivial. It looks it looks kind of like the differential equations that we solved when we were solving the one-dimensional heat diffusion equation, right? So we had heat diffusion if it was steady state with generation, that would be like 0 equals d squared t dx squared plus q dot over rho Cp. something like that. I think that's right. So it's the same kind of form. We have a second order differential in temperature, and then something that has a Q dot. The difference is that that thing that has a Q dot, now this part, that has a temperature in it too, which is going to change how we have to actually solve it. But it's the same kind of idea. If you think about what this equation, the blue equation, what that meant physically. Okay, so heat is going to be diffusing. That's the d squared t dx squared. And then the q square, or the q dot, is heat being generated, or I guess taken away by some case. So it's the same kind of thing. You have the d squared, this first term. This is heat diffusing through the object. And this is how heat is removed from the surface by convection. You have kind of the exact same idea, basically. So let's solve an example problem. Let's say, for our example, we have a surface here, which is a silicon chip, and the temperature of our chip, we're trying to design it so that it's not greater than 70 degrees. So we'll do our analysis at exactly 70 degrees. Okay, we're going to cool this by using fins. So we'll look at just one fin. This is aluminum, where K equals 180 watts per meter Kelvin, the thermal conductivity. The dimensions of this, so that length is, well, I guess I can draw it with a different color. Okay. So this length here in blue is 15 millimeters. So it's pretty short, 1.5 centimeters. It's 3 millimeters thick and 20 millimeters wide. Okay, we have, well, we can put axes on the problem. So we'll put the origin at the base, call that the x direction, down the length of the fin. And then we have convection happening at the surface of the fin. So the convection is happening the same everywhere. So I'll draw it. So HC is 100 watts per meter squared Kelvin. And convection is happening with air at 20 C. Okay, so this is blowing along the fin, again, on all the surfaces. So we might ask ourselves, right, if you're designing this silicon chip, like a computer chip, you need to keep it under a certain temperature, but that chip has a certain power, right? You might, I don't know what my laptop chip is, maybe it's like 7 watts or 15 watts or 30 watts or something like that. There's going to be some power associated with it. So we need to be able to keep it under the right temperature. We have to be able to dissipate that power and still have it under the temperature that we need. So if this is a 30-watt chip and we need to keep it under 70 degrees, when the chip is at 70 degrees, we have to be dissipating 30 watts of heat. So we might ask how much can this one fin, how much heat can this fin dissipate? And this might tell us how many of these fins we actually need in practice, right? If we need 30 watts of heat transfer and this one fin gives us 3, then we would need 10 of them. So we can scale it like that after the fact. So our equation 0 equals dx of ACK dt dx. So the first thing that we can do solving this, those can come out. So if AC and K are both constant in X, so the fin is a rectangle, it's not getting smaller, it's not getting bigger, it's a rectangle. That's not always going to be the case. But it is in this case, so that can come out. Then we would get 0 equals ACK d squared T dx squared minus P HC T minus T infinity. Okay, so this is our kind of our starting equation. We need boundary conditions though. So the first boundary condition, okay, what would be a boundary condition at x equals 0? At this base, that would be x equals 0. So what do we know about the temperature there, or the slope of the temperature there, or something else that might help us with a boundary condition?
That x equals 0 at 70.
Mm-hmm. So we're saying that we're kind of limiting the tip or the chip temperature. We're limiting that to 70 degrees and saying it shouldn't go above that. So we're going to say, okay, so at the surface, at the chip, it's going to be 70. So T 0 equals 70 degrees C. What about our second boundary condition? That would be something now not at the top surface, that's going to be something here at this bottom, at the tip. What would be a reasonable boundary condition at the tip? So there are a couple different ones that I could imagine. One would be that, say this fin is super-duper long. Then the tip is going to eventually come to the same temperature as what like T infinity is. So then it would be maybe 20 degrees C. There are other things that could maybe make it, so one could be like it's just the fin is really long, so we dissipate all of the heat and it's cold at the end. Another one might be, maybe a better one, would be convection. So we could say at the tip, convection is happening because convection is happening everywhere. Turns out that one gets messy, so we're not actually going to solve it analytically. You can, but we won't do it in class. So the one that we'll do is say, we'll say the tip is small, right? It's not a big area. It's 60 square millimeters, but most of the convection is happening on the sides, right? So you have, right, like most of the convection is happening at these sides and at this side. So the tip is small. It's probably not a lot of heat transfer there because it's small. So what we're going to use is we're going to say that that this has an insulated tip. That's not true, really, for like this example problem. I mean, I guess I can make it true because I'm just writing the example on my page, but that wouldn't be a very great realistic boundary condition. But we're going to use it for this because it makes the math easier, and then we'll look at the results of, okay, if we had a different boundary condition, like if we had convection, what would the math be then, like just final answer. So if we had an insulated tip, that would be dt dx, sorry, at x equals L would be 0. Okay, so we use that because it simplifies our math. And as you'll see, the math is ugly enough even with that. So, so it's worth using it. Okay. So our first step in solving this is we're going to start trying to smash things together and simplify them. So our first step can be just looking at d squared t dx squared equals p hc over ac k t minus t infinity. You can see that it's this jumble of variables: the perimeter, convection, cross-sectional area, thermal conductivity. Those variables don't matter independently. They actually only matter as a group. So if you change the cross-sectional area and make the cross-sectional area smaller, but then make the perimeter wider, like those can offset each other and make no functional change to how the thing is actually performing. So this group of variables is what's important. It's not actually any one of them by themselves. The other thing that we're going to do is say, I don't really want to deal with having that like t minus t infinity all over the place. So we're going to swap it out and change that into a single variable. So we're going to do a change of variables. Because it's not the actual temperature that matters. It's the difference in temperature between the fin and convection. So we're going to let theta equal t minus t infinity. So if theta equals t minus t infinity, then t equals theta plus t infinity. So everywhere where we see a t, we can plug in theta plus t infinity. So we can do now d squared dx squared theta plus t infinity equals p hc over ac k theta. Because this is an addition sign, we can split it up and do those two differentials at the same time. And the t infinity will go away because t infinity is a constant. So you take the second derivative of a constant and that equals 0. So this just simplifies to d squared theta dx squared equals p hc over ac k theta. Okay, so that's simpler to deal with. Let's get rid of this big, ugly jumble of constants. Instead of having 4 constants, they don't matter independently, so let's just have 1. So we're going to choose kind of a happy value because I know where this is going, and even if you don't. So we're going to let m squared equal p hc over ACK. I'll box that because we'll end up using that in our solution. Because we're going to eventually have to get back to our original problem to actually get real numbers and stuff. But if we do this, this gives us d squared theta dx squared equals m squared theta. Okay, why would we do that? Have you ever seen, so the whole strategy was let's get something that we already know the answer to. Have you ever seen this differential equation before? The answer is yes, and you already know the answer, which is great. So what would be the answer? So this is something that if you take the derivative, this is a function, you take the derivative twice, and you get back the same function with a constant squared in front of it. What type of function, if you take the derivative 2 times, you get back itself, and then maybe there's a constant in front of it. An exponential function. So if you take an exponential, if you take the derivative of that, you get an exponential, but then the constant comes down in front. And if you take the derivative again, you get the same thing, but then the constant comes down in front again. So the general solution to this would be theta. So there are going to be constants in front of here, but it's going to be an exponential e to the m x plus c2 e to the minus mx. So actually both e to the mx and e to the minus mx, both of those work because you're doing the second the second derivative, right? So if you did it for this first part, m comes down 1 time, you do the second time, m comes down the second time, and you get c1 m squared e to the mx. For the second part, same thing. This time minus m comes down, but then minus m comes down again, so you get the exact same thing. So we got it in a way that we already know the answer to it, which is always the best way to do math, especially calculus, right? Always the best way. Okay, so this is our general solution. Then how do we find C1 and C2? We have to find those with our boundary conditions. So our next step is to determine from our boundary conditions. So our first boundary condition, and our boundary conditions are going to have to change a little bit, or we'll call it, I guess, BC1. So BC, boundary condition 1 was T at x equals 0 equals 70 degrees C. So this gets changed because we changed from temperature to theta. We'll call this theta evaluated at x equals 0 equals theta B. So this is the delta at the fin base. Okay. Our second boundary condition. Just became, so that was dt dx evaluated at x equals L was equal to 0. So that becomes d theta dx equals 0. Okay, so let's actually use these boundary conditions now with our general solution. So we would be evaluating, so at x equals 0, we'll use BC1. So this is BC1. So theta B was C1 e to the 0 plus C2 e to the 0. So theta B equals C1 plus C2. Or we can flip that and say that C2 equals C1, or sorry, C2 equals theta B minus C1. Now our second boundary condition is at x equals L, saying that the derivative equals 0. So d theta dx evaluated at x equals L equals 0, which would be equal to, so we're taking the first derivative, so m is going to be coming down. So we have m c1 e to the ml plus m c2 e to the minus m l. So for this to work, then we have C1, right? The m's can cancel out, so C1 e to the ml must equal C2 e to the ml. Okay, so we have kind of these two different equations. We have this equation up here and this equation down here, so we can combine them together. So then that would be, right, C1 e to the ml equals theta b minus C1 e to the minus ml. Okay, we would get, yikes.
Supposed to be C1 e to the ml equals C2 e to the minus ml.
Yep. Yeah, that's supposed to be a minus. You're right. Yeah, so we get this kind of like mirror solution where you have an e to the ml and e to the minus ml. You get both of the exponential terms. So we would take this and divide both sides by e to the minus ml. So if we're dividing both sides by e to the minus ml, that's going to cancel out on the right side. And on the left-hand side, this will give C1 e to the 2 ml, right? Because that's dividing by a negative is the same as multiplying by a positive, so we add the exponentials, right? So instead of, we have e to the ml times e to the ml, that's e to the 2 ml. Equals theta b minus C1 And then we can simply do some algebra. I'll skip a step, but we'll say that C1 equals theta B over e to the 2 ml plus 1. Okay, or I guess we'll not box that because it's not that important, but put it in brackets because it's a little bit important. Okay, so we have that for C1. C2 was equal to theta B minus C1. So that equals theta B minus theta B over e to the 2 ml plus 1. And we can do some, okay, right, if we want to get this over a common denominator instead of having these two different parts, we could multiply the top and the bottom of, we would multiply we would get this over, so this would be theta B e to the 2 ml plus 1 divided by e to the 2 ml plus 1 minus right? So C2 gets a little bit ugly. Then we could smash these together. We could then simplify a little bit more. Again, I'm going to skip some steps, but we could simplify to C2 equals theta B over 1 plus e to the minus 2 ml. Okay, so it takes a couple steps, more algebra than I think we need to go into. But you get, again, kind of this symmetric formation where you have a, like, you have e to the 2 ml plus 1 and e to the minus 2 ml plus 1. So you get kind of a symmetry in the coefficients, which is kind of neat. But then that only gives us our C1 and C2. So now we have to throw those back into the general solution to get our final answer. So our general solution, put C1 and C2 into the general solution. So that would tell us that theta be equal to theta B over e to the 2 ml plus 1 e to the mx plus theta B e to the minus 2 ml plus 1 e to the minus mx. Okay, so that's our final solution. We can simplify it a little bit further because cosecant, cosh, can be represented in terms of exponentials. So cosh is e to the x plus e to the minus x over 2. That's the cosecant function. So if we wanted to say, okay, let's represent this instead of exponentials, let's represent it with cosecant. It'll actually make it a little bit more straightforward. We could write that, right, theta divided by theta b is equal to, right, that would be e to the mx over the 2ml plus 1 plus e to the minus mx this again will we'll do some algebra magic. That would go to cosh of m times L minus x divided by the cosh of ML. So it actually simplifies down quite a bit. So our final solution, theta over theta b, is cosh m L minus x over cosh ml. Right, this is with m squared equals p h over ack, that collection of constants. So that's really all that we need to find. This finds us the temperature profile, right? It's finding us the temperature as a function of x. So it's not necessarily exactly what we want if we want to find how much heat the fin dissipates, but it's part of the way there. You need to know the temperature profile before you can calculate heat transfer. Okay, so this would be our general solution. We could find m squared equals p h over ack. This would be, what is the, if we go back up to our example, a long ways ago, our fin was, so the perimeter is 23, 23, so our perimeter is 46 millimeters. Our cross-sectional area is 60. So this is 46 millimeters by 60 millimeters squared. Our thermal conductivity is 180 and H is 100. So this is 100 watts per meter squared Kelvin. This is 180 watts per meter Kelvin. Okay, so we'll get that into, so this will be 46 times 10 to the negative third meters times 100 watts per meter squared Kelvin divided by 60 times 10 to the negative, not negative 3 because we squared our millimeters. So this would be times 10 to the negative 6 meters squared. Okay, so m squared, if we calculated it, would be equal to 426. So m is 20.64. Okay, So it's going to be this value m is going to be a unitless number from our collection of constants. So it doesn't have any units because it's a ratio of things where all the units will cancel each other out. So you end up with watts per Kelvin on the top, watts per Kelvin on the bottom. That all cancels out. So the kind of neat thing is that it's not a single value that matters. It's this kind of unique collection of values. If we wanted to plot the temperature everywhere in the fin, we could use this equation here to do it. Sometimes we might care about that. Maybe more often we probably don't care about that. We care about, like what we asked at the beginning, how much heat can we actually dissipate with this fin? So we can say something interesting from conservation of energy. So we are typically interested in the total heat dissipation by the fin, right, which we'll label as Q fin. So from the first law, of energy, we can actually say something kind of interesting. So we go back up to our picture as I explain this. So we want to look at the total heat that's being dissipated everywhere in the fin. That's not super straightforward to actually look at. We could take the temperature everywhere and the convection coefficient, and we could integrate the two, and it would be ugly and gross. We could do that and get it. But the cooler thing is with the first law, the total amount of heat that's leaving must be equal to the total amount of heat that's coming in. So the total heat that's coming into the fin at the base has to be going somewhere. Where is it going? Oh, it's leaving. So we don't have to actually look at the heat being dissipated at the surface of the fin. We can just look at how much heat is coming into the fin at the base. So if we look at that, so Q greater than black, Q fin must be equal to Q evaluated at x equals 0. So the total heat leaving the fin must be equal to the total heat coming in. Right, so that is the heat okay, which that gives us a more tractable problem to solve. So we would have, okay, so Q evaluated at x equals 0 would be equal to minus ACK times d temperature dx evaluated at x equals 0. So that would be equal to, right, minus ACK times d dx of this whole big ugly thing. So we would basically take our whole equation for temperature and jam it into this. So we would get T infinity plus TB minus T infinity, and I'm going to run out of room here. Let me pull this down to a different spot because this is going to get ugly. Okay. Minus T infinity, then cosh M L minus X divided by cosh ML, all evaluated at X equals 0. So to do this, you would have to look up what's the derivative of cosh. So dx of cosh u equals du dx hyperbolic sine of u, right? So cosh and sinh work like sine and cosine, where if you take the derivative, it switches from cosh to sinh, and then you have the derivative of the inside part that comes down in front, okay? So that's all this is saying. Like, you try to take the derivative of cosh, it flips to sinh, but then you have the derivative of the inside stuff come out. I promise we're almost there. Okay, so if we did this, we would get that Q fin, right? Because these are the same thing. This equals minus ACK. This is some of the constants, T B minus T infinity over cosh ML. So that would be our constants. Then we would have d dx of cosh ML minus x. Okay, minus k or minus AC k then the derivative of the inside stuff would be minus m, would be a negative m, and then it would flip from cosh to sinh. So this would be hyperbolic sine of ML. Again, we're evaluating this at x equals 0. So that's why the x ends up going away, because we evaluated at x equals 0. All right. Kind of gross. We're almost there. We're still not quite there. We have a sinh over cosh, just like sine over cosine can give us tangent. Sinh over cosh can give us tanh, I guess. I don't know how to pronounce it. So this would be Q fin equals ACK TB minus times M, because we have, so the two negatives cancel each other out. We have a negative AC and a negative M, times TB minus T infinity hyperbolic tangent of ML. I can make my equal sign better. All right. It's a journey. So I wanted to derive this one in full, in part, right? You're glad, hopefully, that we didn't do the convection one. I'll show you what the answer is for that later, and you'll be even more glad. But the cool thing is how few terms actually end up mattering, right? So there's the I guess this term M, which is our collection of constants, that matters. The difference between the base temperature and the temperature far away, so that is proportional to that. So if we have it's just linear. So we can like double or triple the heat dissipated by doubling or tripling the temperature difference. So it's going to be directly linear, which is kind of maybe a result that you wouldn't expect. I mean, maybe it makes sense because that's what convection is too. And then it's dependent on the cross-section area and the thermal conductivity. So how do you make, how would you improve convection? Well, you could make it like higher thermal conductivity. That's why typically systems with fins typically are aluminum, because aluminum has a thermal conductivity of 180, which is fairly large. You could go to like copper. Copper has a thermal conductivity of like 400, so you could double how much heat you're dissipating by going from aluminum to copper, but copper is a lot more expensive. But knowing that it's pretty much like you have this value for K, how this works. That's if we wanted to plug in our final answers for our actual example problem, that was 4 pages ago in your notes. This would be Q fin equals, and then we would just start plugging in our different constants. So our cross-sectional area would be 60 times 10 to the minus 6 meters squared. Thermal conductivity is 180 watts per meter Kelvin. M was 20.6. 20.6. Our temperature difference was 70 minus 20. 70 C minus 20 C times the hyperbolic tangent of 20.6 times our length, which is, times our length, which is, what was it, 15 millimeters? 25 millimeters? It was 25 millimeters, right? 15 long? Okay. So 15 times 10 to the minus 3 meters. Okay, so we could plug all of that in. We would get Q fin is about equal to 3.3 watts. Okay, so if we actually wanted to go and solve our problem. So that's one way to quantify how good our fin actually is. This fin dissipates 3.3 watts of heat. I don't know if that's good or if that's bad. You could tell some things about it. Like if you wanted to dissipate 10 watts of heat, if you had 3 fins like this, that would do it, right? So you can tell some stuff. Oftentimes we're interested in not doing, in not doing all of that math, but also in just quantifying like, how good is this? It's not, for these kind of systems, it's not super clear how we actually connect an analysis like we just did to like how good the thing actually is performing. In engineering, a lot of times we care about how good is this thing that we just designed. So there are a couple different ways to quantify it. So the first way would be, okay, so we're looking at this. So there's our base, T equals 70 C. We have our fin coming off of it. Like that. We have convection happening here. So this was T infinity equals 20 C, and H is 100. So same as what our same problem. We could look at the first way, we'll call the fin effectiveness, which the fin effectiveness compares with and without a fin. So if we just like pop that fin off, there's still going to be convection there. There's still going to be heat transfer. We want to compare how good is it with the fin versus without. So our effectiveness, epsilon F equals Q with fin divided by Q without our fin, right, which is equal to Q of our fin divided by the area of the base times H theta B. So that would be just convection at the fin base. So this part is so if we pop the fin off and we just looked at convection over that area, how would that work? So that would be one way to measure the fin, to measure our fin performance. This would be, so EF equals, well, I'll box it here so that we have it area base H C theta B. And if we were to calculate that for our fin, that would be 3.3 watts divided by the area of our base. This is the cross-section area. So 60 times 10 to the minus 6 meters squared times 100 watts per meter squared Kelvin times 50. 50K is our temperature difference. So this would equal for our fin 11.3 or 11.13. So one way to quantify it would be to say, how good is it without? Well, it's 11 times more heat with that little, even though our fin is relatively short, it's only like 1.5 centimeters by 1.5 centimeters long. It's relatively short, but it enhances the heat transfer by a factor of 11. So you can see obviously how effective something like this, even a small one, if we make it out of a highly conductive material like aluminum, works really well. Typically, just like a rule of thumb, so typically you're not going to actually be using a fin in a design if the effectiveness isn't at least a factor of like 2. If you can't at least double the heat transfer, you probably don't want to use a fin. There are probably other ways that you have to redesign the system to enhance heat transfer if you're going for that. And usually, like, the higher the better. That's not totally true because you always have other design considerations. Like for this heat sink, you're going to be thinking about, okay, I'm space limited. If I'm, if this is a computer chip, how big can the fins actually be? Are there other ways to do it? So you're always limited by other design considerations as well. But the higher the better generally, because usually you're putting fins on something to try to cool it down. So if you can cool it down more, that's better. The other way to think about it, so this is comparing it, like how good is it compared to not having it there? Another way to think about it though is how good is this compared to a perfect fin? How good is it compared to not having a fin? How good is it compared to the best possible fin that we could have? So first we have to define what a perfect fin would be. It would be made out of some material that has an infinite thermal conductivity. That would mean that the entire fin, right, basically any heat is going to go into that fin. The entire fin ends up being at the base temperature. Whatever that base temperature is. So for this fin, our fin, we call this the fin efficiency. Eta F. So we have these two measures. We have the fin effectiveness, how effective is it at transferring heat? The fin efficiency, how good is it compared to a perfect version of itself? This would be equal to Q of the fin divided by the area of the fin times HC theta B. Okay, so they're really close equations. The difference is the different area. So the first equation, we have the area of the base. This equation, we have the entire surface area of the fin. It's approximately equal to P times L. That misses the tip. But usually, well, this misses the tip, but this is the extra surface area that you get. Because if you didn't have the fin there, you would still have the same, like the cross-sectional area would still be there. So this is the extra surface area. So in our example problem, this would be 3.3 watts divided by the 46 times 10 to the minus 3 meters times 15, 10 to the minus 3 meters times 100 times 50K. So this is 3.3 watts divided by 3.45 watts. So our fin efficiency ends up about 97%. So this is a good measure of like whether your fin is actually, whether you need to make it out of a different type of material. Like this, you could switch from aluminum, which has a high thermal conductivity, to copper, which has an even higher thermal conductivity. But this tells you you're not going to gain anything because you're already basically maxed out. The last thing, and where I'll end, is just to show just to show like what so our book, like when we did thermal resistance, our book had a table where it like took all of the results from all of the different geometries and summarized them and smashed them into a table. The book does the same thing with fins. So you can see, okay, let me get a pen here. So you can see this case B, that's the one that we just did. So that says the tip condition, what's happening at the end of the fin. That was adiabatic, which is what we said. We said it was insulated, adiabatic. Those are the same thing. And it gives us, okay, what is the temperature distribution? Theta divided by theta B. And what is the fin heat transfer rate? And this gives it as capital M tanh ml. Just knowing that capital M is equal to this. The one thing, and I'm going to post this, so we'll use this. Theta B is not under the root. I don't know why they write it like that, but when I hand it out, I'll make note of that too. But theta B is not under that square root. But you can see, right, convective heat transfer at the tip, if we have that, we get that big ugly equation. So we get a whole bunch of extra whatnot. But it turns out if we, like, once you have the equation, it's actually not that much harder to use. It just is more buttons in your calculator. Sometimes we'll have a prescribed tip temperature. Like if you had, for example, like two different things at different temperatures connected by something else, you could have each end of the thing at set temperatures and heat traveling across, say, like a rod or something connecting two objects. You could figure out the heat transfer rate from that. And then the last one, you could have an infinite fin where the temperature at the end of the fin has become the surroundings temperature. So that's the easiest one. That's just going to be, there's going to be just an exponential decay of temperature down that fin, right? E to the minus mx, just an exponential decay. And the fin heat transfer rate then is just this term, capital M. So we will use this, the homework that's posted for next week. I think you can probably solve most of the problems now. It's all fins. There's some that you won't be able to solve until after Tuesday. We'll talk about, this is all with, like, all of this stuff is for kind of simple cases where you have like a square fin sticking out of something. If you had like a circular thing, or if you had something that's like a triangle, something that's changing area, then you have to do things totally differently. The good thing is we won't actually do that. We'll just kind of look at the results and be able to use these quantities of fin efficiency and fin effectiveness, really fin efficiency, to be able to do that, where we can say, you know, well, how is this compared to a perfect fin? So I think because it's nice to do every now and then, well, I think we'll end there for today. So we have a couple minutes left, but that's fine. We'll see how, see how this fits in our next homework assignment. Like I said, I think you do have enough stuff to start if you want to. You can probably get some of the basic stuff done. right? So what you're basically going to do is like jump to this table, and I'll post this on Moodle. You'll jump to this table and say, what's the end of the fin doing? And that's where you're going to start. So you kind of pick which set of equations you want to use based on what's happening at that tip. So we'll end there. You get a couple extra minutes because it's Wednesday, right? Thursday. Yeah, so I can either collect it in like now, you can just hand it to me, or you can upload it onto Moodle. Thank you, sir.